Hello, I welcome you all to the session on the discussion of GATE 2022 paper. We are going to discuss only the questions on aerospace propulsion. Okay, so we'll be doing GATE 2022 Aerospace Engineering. Only the propulsion part of the paper. I am Reginald. I am a faculty member of propulsion at the JNF Academy. So I welcome you all to this discussion on the solutions for the GATE 2022 paper. Right. So first with the 1-mark questions. This was question number 23 in the master key. The region of the highest static temperature in the rocket engine and the region of the highest heat flux are the highest static temperature occurs in the combustion chamber and the highest heat flux occurs at the nozzle throat. Because if you look at the rocket thrust chamber, you have the combustion chamber and then you have the CD nozzle. So everywhere in the nozzle, you know that the velocity increases. So as the velocity increases, at the inlet of the nozzle, you have the highest static temperature and zero velocity. So as the velocity increases, you see that the static temperature decreases because the stagnation temperature is going to be a constant for a nozzle. So definitely at the entry to the nozzle or at the combustion chamber, that's where you have a very low velocity and hence most of the energy is as a static temperature. As the gas expands through the nozzle, because the total energy or the stagnation temperature has to be a constant. You know, stagnation temperature is static temperature plus V square by 2 Cp. So as this increases, this comes down because T naught has to be a constant. So definitely the answer has to be combustion chamber where the static temperature is the highest and the nozzle throat is where the heat flux is the highest. The next question that we will discuss is question number 30. Again, it is a 1-mark question. This is a multiple select question. Okay, this is not a multiple choice question. This is a multiple select question, meaning there are more than one correct answers. You can see from the letter S here. A high pressure ratio multi-stage axial compressor encounters an extreme loading mismatch during the starting. Which of the following techniques can be used to alleviate this problem? So to reduce this loading mismatch during the starting, the techniques that are suggested are by using blow-off valves, by using a multi-spool shaft, as well as using variable angle stator vanes. Blade cooling has to do with turbines. Okay, blade cooling is one of the techniques which is used for axial turbines, not for axial compressors, because in turbines, the main issue is with the temperature. Very hot gases from the combustion chamber are entering to the turbine. So, and the turbine rotor has to rotate. So a rotating component which is exposed to such heavy temperatures, that's a big problem in a turbine. So cooling is a problem which is related to axial turbines, especially the rotor blades. But this has nothing to do with the axial compressor. But all the other techniques that are mentioned are standard methods for reducing this loading mismatch for an axial compressor. And if you want a good reference for this, you can look at Cohen-Rogers, the textbook Gas Turbine Theory. By Cohen and Rogers. It's a very standard book. This is the book that we refer to for teaching propulsion here. If you look at Cohen-Rogers, the same words are there. Okay, this is taken from compressor characteristics and off-design conditions. So you see that for reducing these effects, I think these same words you can see. Blow-off, they have explained what is blow-off. Then you can see the word multi-staging. Okay. So you have, I think the last, yeah, a twin spool configuration. So you can have multi-spool And the third reason, you can read it, you have variable status. Okay. So it's very clear that they have kind of taken the question from this book. You see that to satisfy the off-design performance of high pressure ratio compressors, the same wording as in the question. So I request you to go through this. I don't want to read all these paragraphs here, but I've given the reference. Please go through this passage so that you will get an idea of the questions that is asked in the GATE exam. So the correct answers would be 3, B, C as well as D. A is not the right answer. I hope you know what is an MSQ question. Only if you mark all the 3 answers, you will be given 1 mark. If you do not answer these 3 correctly, for example, you answered only 2, or you answered 3 wrong ones, or you answered only 1, then you get a 0. There's no negative marking here. If you mark B, C and D correctly, then you get 1 mark. If you mark anything else, you get a 0 mark. Okay, proceeding with the next question. This is the third question, third 1 mark question that was asked. Again, a very simple question based on a turbofan engine. So this was question number 34 in your master paper. The data given is the bypass ratio for the turbofan engine is 9, and the exhaust velocity of the hot jet is 1.5 times the exhaust velocity of the cold jet. So this ratio alone is given, and you're given that the air fuel ratio is 0.03. These are the only data that are given for the bypass turbofan engine. Now, we know the thrust equation for a turbofan, and also another keyword is static test. It's a static test. So it's not a test that is conducted with the turbofan engine flying in the air. Probably you're conducting it on land and you're holding the turbofan engine static. So it's a static test. That means the entry or the air entry to the fan or to the engine is going to be 0 at 0 velocity. So very importantly, because it's a static test, we have CA equal to 0. By the way, these notations that I'm using are just matching with Cohen-Rogers. So I'm using the same textbook. If you want to know what is CJC, CJH, I suggest you look at Cohen-Rogers, the textbook by Cohen-Rogers. Now the equation for thrust is the hot thrust plus the thrust from the cold nozzle. The thrust from the hot nozzle can be written as m dot H plus mass flow rate of fuel into CJH minus m dot H into CA. This would be the thrust from the hot part of the thrust. Or let me write it like that. FH is this. Likewise, the thrust from the cold jet will be equal to m dot C into CJC minus CA. CA is the flight velocity, CJH and CJC are the exhaust jet velocity of the hot jet and the cold jet. And m dot H is the mass flow rate of air through the hot engine. M dot C is the mass flow rate of air through the cold engine. M dot F is the mass flow rate of the fuel. Now they have asked what is the ratio of fan thrust to the thrust from the core engine. So I have the turbofan engine here. Anyway, they've asked what is the ratio of the fan thrust, the cold thrust to the hot thrust. So this is given by m dot C into Cj minus Ca divided by m dot H into 1 plus F. I'm taking I'm bringing the air fuel ratio into picture into CJH minus m dot, or I can take the m dot H outside, minus Ca. This equation is self-explanatory. I think you would have understood it. Now Ca is 0 because it's a static test. So you can cancel off the Ca, and m dot C by m dot H, that is the bypass ratio. So we know bypass ratio is m dot C by m dot H. So instead of these terms here, I'm going to write B there. We have CJC divided by 1 plus F into CJH. Now this equation simplifies. First thing is bypass ratio is given. So the m dot C and m dot H, that ratio is replaced by B. Ca is 0 because it's a static test. And then the remaining terms are all given to us. So I'm just going to put the data. Bypass ratio is 9. CJC by CJH is 1 by 1.5. So I'll write it as 1 by 1.5. And 1 plus F is 1.03. Okay. So then the answer will become 9 divided by 1.03 divided by 1.5, which equals 5.825. Okay. So because it's a ratio of two thrusts, there's no unit. So this is the ratio of the cold thrust to the hot thrust. It's 5.825. That's the ratio. Now you see that it's a turbofan engine. So the bypass ratio is 9. That means the mass flow rate through the bypass duct, that's 9 times the mass flow rate through the core engine. Hence, a large thrust is produced by the cold jet. Almost 5 times, 5.8. So almost 6 times of the thrust of the hot jet is equal to the thrust of the cold jet. So this is FH. So the answer is 5.825. I hope they will not give a lot of interval or range will be very short because F is given. Okay. Suppose you did not take that account of F. Let's see what the answer we will get. Suppose you just forgot or ignore F. If you did 9 by 1.5, then the answer you will get is 6. Correct? So this will not be included in the key as per what I am expecting. They would always, because they have mentioned the air fuel ratio, they'll want you to account it for in the answer. So definitely the range will be such that 6 will be excluded. So if you marked 6 as the answer, probably you will not be able to get marks. That's my guess, but let's see what the key that they're going to upload. So if you're very close to this and you're below 6, then probably you're going to get full marks. Okay, so we are done with the third 1 mark question. Now we are going to the fourth 1 mark question. This is the last 1 mark question asked in propulsion. Totally we had 4 questions. This is question number 35. In question number 35, it's about a single stage turbine. It's an axial flow single stage. It's a single stage of an axial flow turbine. In a single stage turbine, the hot gases come out of the stator nozzle, stator or the nozzle at a speed of 500 meters per second. It's also shown here in the figure, 500 meters per second at an angle of 70 degrees. The design speed of the rotor blade is 250 meters per second. So you know that the rotor blade speed is 250 meters per second at the mean blade radius. The rotor blade angle is beta at the leading edge. So you know the angle that the rotor blade makes with the leading edge is beta, and it is the design condition. Now they have asked what is the beta. You have to find what is the angle beta. Now the clue is velocity triangles, because this is the absolute velocity at the entrance to the rotor, and we know the velocity of the rotor. We know the blade speed. This is the direction of the relative velocity. So by looking at the data given, you have to guess that it is only velocity triangle that you have to solve. Okay. So I'll try to draw the velocity triangle as it is given in this direction, the same inclination I'll try to draw. First of all, the blade speed. The blade speed is 250 meters per second. So let me mark the blade speed in the same direction. 250 meters per second. U is the blade speed. Then the absolute velocity is 500 meters per second. So this is the absolute velocity, 500 meters per second. I use the letter C to represent the absolute velocity. Now the definition of relative velocity is, it is the velocity of the fluid relative to the blade. So here V is the relative velocity, C is the absolute fluid velocity, and U is the blade speed. So the definition of relative velocity is, it is the velocity of the fluid relative to the blade. So V is C minus U. And if you want to complete the triangle according to this vector equation, the relative velocity vector is like this. By the way, the tangential direction is this. This is the tangential direction, and this will be the axial direction. Okay, it's shown. This is the axis of the turbine. So let me mark the axial direction here, because the blade angles and the nozzle angles are measured in the axial direction. From the axial direction, this vector, the relative velocity is at an angle of beta. This is the rotor angle. And the absolute velocity is at an angle of alpha, which is given to be 70 degrees. Now, once we did the velocity triangle, it's all from the velocity triangle that you have to find beta. So let me do the same velocity triangle here in a larger scale. So we have u equals to 50 meters per second. And we had c, which is 500 meters per second. And the closing side of the triangle is is v. You're supposed to find, you need not find v, but the inclination of v from the axial direction. So this is the axial direction. This will be the tangential direction or the world direction. Now, if you resolve c, we know that this is CA. This is also equal to VA. And if you resolve C in the tangential direction, you know this is CW or C theta. And this will be V theta or VW. Okay. So you can resolve both the absolute velocity as well as the relative velocity into the axial component and the whirl component. For both the velocity vectors, the axial component has to be the same from the velocity triangle, but the whirl component is different. So from the velocity triangle, if this angle is beta, we know tan beta is VW by VA, the whirl component of the relative velocity by the axial component of the relative velocity, or beta equals tan inverse of VW by VA. But from the figure, we know that VW is nothing but CW minus U, correct? Because CW is the whole thing. If you subtract from the blade speed, you get VW. And VA is nothing but CA. I'm replacing V data because I don't know the relative velocity, but I know the absolute velocity and the blade speed. So from the data that I know, now we can plug it in here. Tan inverse of, what is the whirl velocity? The whirl component of velocity, because I know this angle is 70 degrees. I know this angle is, or this length is going to be 500 sine 70 minus the blade speed. The blade speed is 250 divided by 500 cos 70 degrees. Okay. The axial component is 500 cos 70. The whirl component is 500 sine 70. All you have to do is 500 sine 70 minus 250 divided by 500 cos 60, 70. And the answer happens to be 52.122 degrees. Because they have asked to round to 1 decimal place, the correct answer would be 52.1 degrees. I think plus or minus 1 they will give you. For example, 52.0 to 52.3, they may give an allowance by plus or minus 0.1 degree, but more than that probably they will not give an allowance. But this is the exact answer. Okay, it's a very simple idea. I took a lot of time, but during the exam, if you are clear with the velocity triangles, it doesn't take much time. Okay. So you should, by looking at the data, you should be able to figure out that it's a question based on velocity triangles. And two velocities are known, the absolute velocity and the blade speed are given. You are asked some information from the relative velocity. So try to construct that information that you require from whatever you know. You easily end up getting the answer. And it's a very common question in GATE exam to ask question from the relative velocity and from the velocity triangles. Every year, at least one question comes from velocity triangles. Velocity triangle idea is a very important idea in propulsion. So with this, we see 1 mark questions are over. Basically, they took one theory question, a theory question in rocket propulsion, a theory question in axial compressors. Then they took 2 numerical questions for 1 mark, one from a basic turbofan thrust calculation and a very basic question from the velocity triangle of an axial flow turbine. So I feel this is a very standard kind of way of giving the paper, 2 numerical questions and 2 theoretical questions in 1 mark. Now let's proceed to the 2 mark questions. The first 2 mark questions was a little surprising for me because it was very simple. It could have been asked in 1 mark also, but they gave a weightage of 2 marks for this question. It's a very basic fundamental question. Even if you know a little bit of chemistry, you'll be able to answer this and get 2 marks. So people who kind of just went through the last paper pattern without having understood the concepts, you would not have answered these kind of questions correctly. But people who gave focus to fundamentals would have answered all the questions correctly. This is question number 42. This is the first 2 mark question that we are going to discuss. Which of the following is not always true for a combustion process taking place in a closed system? First of all, it's a closed system and it's a combustion process. The total number of atoms is conserved. Yes, definitely in any combustion process, the total number of atoms have to be conserved. The total number of molecules is conserved? No, the molecules can change. Atoms can become molecules, molecules can break into atoms. 2 molecules can become 3, 3 molecules can become 2. Molecules is never conserved in a chemical reaction. Total number of atoms of each element is conserved? Yes. In fact, that's how we balance a chemical reaction. Total mass is conserved? Yes. Because it's a closed system, definitely mass is not going out. The atoms are not going out. Mass has to be conserved. So it's a multiple select question and there are 3 correct answers. Sorry. This is not a multiple select. It's a multiple choice question and the question is about which is not always true. So the correct answer would be option B. The total number of molecules is conserved is not always true for a combustion process taking place in a closed system. To prove something, you have to give a theoretical proof, but to disprove something, you just have to give a contradiction. Let's try to disprove that the total number of molecules is conserved. For example, the basic or the simplest combustion reaction would be hydrogen plus oxygen gives water. Okay, that would be the simplest chemical reaction or the combustion reaction that I can think of. Now let's try to balance. Let's say 2 and 2. So you see the reactants. Okay, the reactants, you see that, or before the reaction happened, you see for 2 molecules of hydrogen plus 1 molecule of oxygen giving 2 molecules of water. So definitely the number of molecules is not conserved. Before the reaction happened, there were 3 molecules, 2 hydrogen molecules and 1 oxygen molecule. But after the reaction is over, you see only 2 molecules of water. So the 3 molecules became 2 molecules. Where did the 1 molecule go? It is not conserved, need not be conserved. As simple as that. Even if you could have thought of this simple counter example in the exam, you could have got the 2 marks. But the atoms are conserved. The number of hydrogen atoms before combustion is equal to the number of hydrogen atoms after combustion. Likewise, every species, the number of atoms is conserved and hence the total number of atoms also conserved. So it's a very simple conceptual question. I think a high school student would have answered it correctly. Now coming to the next question. This was by far a very deep question in this paper. I think the most difficult question as far as I saw, or the most conceptual question is this. It's not very difficult if you understood the thrust coefficient, but if you did not understand the thrust coefficient, you just memorized expressions, you may not be able to answer this in the exam. So this is question number 47. Let me explain the question for you. A rocket operates as at an absolute chamber pressure of 20 bar to produce a thrust F1. So when the chamber pressure is 20 bar, the thrust is F1. The hot exhaust is optimally expanded to 1 bar. So from 20 bar, it's optimally expanded to 1 bar using a CD nozzle with an exit to throat area of AE by AT 3.5. So for this AE by AT, the pressure ratio, the optimal pressure ratio is 20:1. That is 20 by 1 bar. And the thrust coefficient happens to be 1.42. This is the optimal thrust coefficient. Now the same rocket, when operated at an absolute chamber pressure of 50 bar, produces a thrust of F2 with the thrust coefficient of CF2. Which of the following statements is or are correct? It's a multiple select question. So more than one answers could be marked, must be marked in fact. So F2 by F1 is equal to 2.5. CF2 by CF2 is equal to 1. F2 by F1 is greater than 2.5. CF2 by CF1 is greater than 1. Let's try to answer this question. Now, like I told you, it's a little bit deep in the concept. First thing is you should know what is the expression for CF. CF is CF optimal plus, we discussed this during the class. Okay, the thrust coefficient can be written as the optimal thrust coefficient plus AE by AT into PE by POC minus PA by POC. And what is the optimal thrust coefficient? The optimal thrust coefficient is gamma, the Van den Keschow function, 2 gamma by gamma minus 1 minus PE by POC to the power of gamma minus 1 by gamma. Okay, so you observe that the CFO is not a parameter which depends on the chamber pressure directly. Okay, because this ratio is going to be fixed for a nozzle. For example, when you operate the CD nozzle, let's say the rocket nozzle, when you operate it at 20:1, when it was 20 bar and 1 bar outside, this is optimal expansion. Okay, suppose you have 50 bar instead of 20 bar in the chamber. We know by nozzle theory that within the nozzle there's no change. So the ratio of the chamber pressure to the exit pressure will be same as in this case. It will be 1:20. But outside the pressure is 1 bar. So basically what will happen is, though the atmospheric pressure is 1 bar, the ratio of P0 by PE will be the same as the optimal. Okay, so here you saw P0 by PE is 20 by 1. So the same ratio will be there. It will be 20 by 1. So I can find what is PE. PE will be 2.5 bar, right? 50 by 2.5 is the same as 20 by 1. Am I right? 50 by 2.5 is the same as 20 by 1. So what will happen in this case is, when you, in the condition 2 that they have given, within the nozzle, the velocity, Mach number, everything will be identical, but the exit pressure will be 2.5, such that the ratio will still be 20. And because you have a high pressure outside, the gases will now expand further to 1 bar. Okay, there will be expansion wave outside. And then due to this expansion, you get an additional thrust. So this is the additional thrust term. So when you have 20 bar, you have only this CFO. You do not have the contribution because PE is same as PA. PE will also be 1 bar and PA will also be 1 bar. But when you have the nozzle working at 50 bar, the CFO will remain the same, but there will be an additional contribution because of the expansion outside the nozzle. And that will give you a small addition through the thrust. So conceptually, if you know the CF optimum and the additional part, you can easily say that, 1 minute, you can easily say CF2 will be CF1 plus AE by AT into PE minus PA by POC. In fact, the data are given. CF1 is given to be 1.42, if I'm right. Yeah. Specific thrust is given to be 1.42. AE by AT is given to be 3.5. We calculated PE. Remember, 2.5 minus 1 divided by POC. In this case, it's 50 bar. In fact, you can even calculate what would be CF2. CF2 would be 3.5 into 1.5 by 50 plus 1.42. It would actually be 1.525, roughly 1.5. Okay, so the CF2 is going to be 1.5. This is definitely greater than CF1 because of this positive contribution here. This is positive. So you add to CF1 to CF2. So this will be the first result. Now further, they have asked a question based on F2. F2 by F1 is CF2 POC2 AT by CF1 POC1 AT. You know, it's the same nozzle, so the throat area will be cancelled. CF2 by CF1, approximately it's the same, slightly it's greater. But let's put the numbers. In fact, we have the numbers. 1.525 by 1.42 into 50 by 20, which happens to be, this is 2.5, so I'll keep the 2.5. Your 1.525 by 1.42 happens to be 1.074 into 2.5. So you see F2 by F1 is greater than 2.5. It's not equal to 2.5 because of this contribution CF2 by CF1. Because this is greater than 1, F2 by F1 is also greater than 1. So very clearly you can mark the answers which are correct. CF2 by CF1 is greater than 1. Definitely it's not equal to 1. And hence F2 by F1 is greater than 50 by 20. It's not equal to 50 by 20. So the correct answers are B and D. Now another thing is I would like you to refer to the charts. I've taken this from Rocket Propulsion Elements by Sutton, the 2016 edition. You can see figure 3.6 where the thrust coefficient is plotted for gamma equals 1.20. In fact, if you backtrack and I just tried to do this experiment. I just played with it. For the data given in the problem, actually the gamma was 1.2275. Okay. If you know, there are open source internet calculations for isentropic flow available, so you can play with the data. So if you use gamma equal to 1.2275 and AE by AT as 3.5, you get P naught by PE approximately 20. So I figured out what would be gamma for the nozzle that is working. It's approximately 1.2275. So I used gamma equal to 1.2. I took the chart here and 3.5 is here. Okay, let's say 3.5 is here. This is AE by AT, 3.5. If you go to AE by AT, you see that when the pressure ratio is 20, the optimal thrust happens to be 1.42. Do you observe? The optimal thrust is 1.42. So at this pressure ratio, you see that the thrust is 1.42. Suppose you go to higher pressure ratio, let's say 50 as per the problem, with the same area ratio, you see that a very small increase in thrust will be present. The pressure ratio is around 2.5 times. Okay, to create that pressure, you need more propellants, lot of energy. But the addition to thrust that you get is very small. Okay, and from the figure you can see something like 1.5, right? So though you're increasing the pressure from 20 to 50, above the optimum you get very small pressure thrust contribution, which will increase the CF. So this also tells you that the CF is going to increase as you increase the pressure ratio. So if you happen to pay attention to this graph from Sutton, probably it would have been much easier for you to answer this question. Or if you paid attention to the expression for thrust coefficients, you gave the time to understand it, then it's very easy to answer this question. Okay, this is a very nice question, by the way. Now, the other questions are all easy, so I can go faster from now on. The next is the question on the ramjet. This is question number 64. An ideal ramjet is to operate with exhaust gases optimally expanded to the ambient pressure. There are two simplifications. One is ideal ramjet, so the efficiency of components are not going to come. And it is optimally expanded to ambient pressure. So there's no pressure thrust issue coming into picture. So very simple standard analysis is there. If you would have done the analysis earlier, then the exam you would have done got the answer very easily. So for an ideal ramjet, you can use the formula mj is equal to ma. Okay, I'm not going through the analysis for an ideal ramjet. So you can use the formula. The jet Mach number is equal to the flight Mach number. You may think if this is true, there is no thrust, but there is a thrust because the speed of sound is very different. Because ma is calculated at, or the speed of sound is calculated at 220 Kelvin for A, and for the jet it is about 1100 Kelvin. So because the speed of sound changes, the velocity is also going to change. So you can replace this equation as Cj by Ca equals, Cj by Aj is Ca by Aa. C is the speed of the fluid and A is the speed of sound. J refers to the jet and A refers to the ambient, the entry to the ramjet. Now you rearrange further. You want what is Ca? So I can write Ca as Aa by Aj into Cj. And you know what is the speed of sound? It is root gamma A R T A, gamma J R T J, into Cj. There will be Cj multiplying this. R is the same, whether it's air or exhaust gas, R is the same. So you just plug in the numbers, you get the answer. Cj is 1200, square root of 1.4 into Ta is 1100. Sorry, Ta is 220. Gamma J is 1.33 into 1100. Do the calculations, you get Ca equals 550.59 meters per second, which can be rounded to the nearest integer, which is 551 meters per second. So the answer can be written as 551 meters per second. So very simple problem. By the way, this equation that I wrote here, mj is equal to ma, is from the ideal cycle analysis of a ramjet. So if you perform an ideal cycle analysis, one of the standard results that you will end is mj is equal to ma. So I just continued from there to get the answer very quickly. Okay, a simple expected question. This was a very expected question from ramjet. They have asked questions from ramjet in the past also. So this was very much expected and easy. Last question is also a very expected question. This is from multi-stage axial compressors. It is calculations based on the calculation of the number of stages. So again, it's a very standard problem, calculating the number of stages of an axial compressor. So I'm not teaching you anything here. So I'll be a little more faster. The data: inlet pressure is 1 atmosphere. Inlet temperature is 300 Kelvin. And the exit pressure, let me say there are n stages. After n stages, PON must be greater than 5 atmosphere. Okay, it should be a minimum of 5 atmosphere. So let's say it's greater than 5 atmosphere or equal to. So initially, to start with, I'll say PON is equal to 5 atmosphere. Right. So it's a multi-stage compressor. So from first pressure to second, second to third, like that. The final pressure is the nth pressure. If it has n stages, PON is 5 atmosphere or greater. Now the other data given is the mean blade speed. The blade speed is given to be 245 meters per second, and the work coefficient, that is delta C theta by U. This ratio is given to be 0.55. In fact, this is the change in the whirl velocity that's responsible for the work done or the work transfer. That is non-dimensionalized with the blade speed. So it's a ratio which is 0.55. This is for each stage. You can use the standard properties of air, Cp as well as R and gamma. Now you have to calculate the number of stages. The formula for the number of stages is the total temperature rise divided by the temperature rise for every stage. Okay, delta T0 is the temperature rise for the whole stage, for the whole compressor, divided by the temperature rise for the stage. Right. So delta T for the whole compressor divided by the stage temperature rise, that will be the number of stages. Again, this comes from the TS diagram. If you draw a TS diagram, you'll know that the total stagnation temperature is equal to the sum of the stage stagnation temperature rise. So that is the idea behind this formula. Again, it's a very standard question from axial compressor, so I'm expecting that you will remember this formula. Now it's about finding delta T0 and finding delta T0 stage. So delta T0 is T0n minus T01, the final temperature minus the initial temperature. We already know the initial temperature. We have to figure out the final temperature. To figure out the final temperature, let's use the clue. We'll use the process. Compression is isentropic. That's the clue that you have to use. The whole compression process is isentropic. So I can write T0n by T01 is equal to P0n by P01 to the power of gamma minus 1 by gamma. What relation is it? It is the isentropic relation. This is true for an isentropic. So I can rearrange and write T0n is T01 P01 to the power of gamma minus 1 by gamma. Right now I'll take T0n equal to 5. T0 is given to be 300. This will be 5 by 1 raised to the power of 1 by 3.5. And you figure out the answer. T0n happens to be 475.146 Kelvin. Okay. Now you can find delta T0 for the whole compressor. This happens to be 475.146 minus 300, which is equal to 175.146 Kelvin. So this is the first information that you have to find. Very simple. For the whole compression, it is isentropic. So you can use isentropic relations because you know the final pressure. It should be greater than or equal to 5. I've taken now equal to 5 and found what should be the final temperature. This will be the minimum temperature that you have to get in the end. So the minimum temperature rise for the whole compressor has to be 175.146 Kelvin. Now to find the stage temperature rise. To find the stage temperature rise, delta T0 stage, we need to use the velocity triangles. So mainly the data from the velocity triangle is delta C theta. So we all know that delta T0 stage is given by U delta C theta divided by Cp. Okay. So the formula to find the stagnation temperature rise is blade velocity into the change in the whirl component, either it's C theta or Cw. Because of the question, I'll write it as C theta. We know this is the formula. And let me alter this a little bit. I'll write U square delta C theta by U, because this ratio is given. I'll multiply and divide by U and bring that ratio divide by Cp. U is given in the problem, 245 square. This ratio is 0.55 and Cp is 1005. Simple math. You have the calculator, you put it, you get 32.85 Kelvin. Again, very easy calculation. They gave the numbers in such a way that you don't have any issue. They did not even give the velocity triangles information. They directly gave you the work done, the non-dimensional work done, or the non-dimensional change in whirl component of velocity, so that the calculations are easier. So you know that the stage temperature rise is 32.85, and totally after every stage is over, final temperature rise has to be at least 175.146 Kelvin. Now you divide one by the other, you get the number of stages. So delta T0 by delta T0s, 175.146 divided by 32.85 gives me the number 5.33. Now the question itself tells you it is the number of stages required and for the minimum of 5 atmosphere, and they have told you round off to the next higher integer. This is intuitively also correct because we want a minimum of this temperature rise. So for that pressure, you need a minimum of this temperature rise. If it is more, it's better. So let's take it as 6. So 6 stages would be the correct final answer. Now you can check if you have 6 stages, the total temperature rise will be 6 into delta T0s, which is 6 into 32.85, which happens to be 197.1 Kelvin. Now you can backtrap using isentropic relations, or from this you get T0n will be T01 plus 197.1 Kelvin, which is 497.1 Kelvin. So the final temperature known using isentropic relation, you can find the final pressure. I'll not write the details, but if you find the final pressure, you get 5.856 atmosphere. So this satisfies the design that you were requiring. It should be greater than 5 bar. So by the way, this is just to check your answer. Okay, if your answer really makes sense. Yes, the final answer is n is equal to 6. Let me write the answer here. You need 6 stages. So that completes our discussion on propulsion. I hope you are able to follow the discussion that we had here. All the best for your.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.